Hello and welcome everybody to the second day of FMAS. So we will start our day today with the keynote from André Platzer, who first studied in Karlsruhe at KIT, and then he went to Oldenburg in northern Germany to pursue his PhD. Then very quickly he went to CMU, first assistant professor, then full professor, and then he actually just 3 years ago came back to KIT Karlsruhe, and now is the Alexander von Humboldt professor there. And today, André will talk about logic of autonomous dynamical systems. André, the stage is yours.
Thank you. Well, that's my favorite topic, so I'll always be super happy to chat about it. If you have any questions, please do let me know. What is this about? In a nutshell, it's the question if you are, if you are pushing buttons, I guess. In a nutshell, it's a question if you are flying this plane or designing the computer for it, you should notice that there's others close to it. So you need to predict which control decisions are safe, for instance, for aircraft collision avoidance. So straight ahead flights, left turn flights, right turn flights are bad ideas. And only a strong right turn is a good idea because it's the only way out of that. And that's the kind of information you need to know before you even get on the plane. That's the kind of information that the manufacturer needs to know to equip the computer with the appropriate decisions. And should there be other encounters with other planes, you also need to make sure that you figure out a way out of there that keeps you alive. And that's a dynamical systems challenge in the sense that dynamical systems describe the mathematics of change, and the mathematical models describe how the state of a system evolves over time. And your job now is to predict the future of those. Wait a second, that's weird. The point is dynamical systems already describe the future. How can it be your job to then forecast the future? Well, the point is dynamical systems only tell you locally what's going on. For instance, they tell you at this part of the state space, does the aircraft fly a small right curve? At that part of the state space, does the aircraft fly a left curve? At that part of the state space, would the aircraft fly a left path? And your task is then to predict, before you're even off the ground, that the entire path that the system will follow over time will, under every possible circumstances of what the other aircraft will be doing, be far enough away from other aircraft. So something that's predicting the future, but locally, only describing it, your challenge is to predict its behavior remaining safe over time. And that's a bit of a big challenge, unfortunately, but we're happy to pursue it. So in the following way, here's an overview of that. If you have an autonomous dynamical system, I will stay partially on aircraft, partially in cars. Then you write down a model for it, do a proof of safety of the system in our KeYmaera X theorem prover. And then you could say you're done, but you're not really, because now you've done a verification for a proof of safety of a model of a system, but not necessarily of the system itself. So the next step up is you translate this into a compliance monitor for the real system that makes sure that the real system actually fits to the model. Where do you get that from? Well, with our ModelPlex technology, again, using our KeYmaera X theorem prover, which synthesizes the compliance monitor automatically, which you can then transfer back into the real system. And also, if I have time today, I'll talk about how this interacts in a reinforcement learning loop with the actions and observations of the real world. All right, never mind that. One of the applications that we've been looking at is the next generation airborne collision avoidance system developed for the Federal Aviation Administration to replace the TCAS system that's currently operational and equipped on every commercial main aircraft. Responsible for the safety to supporting the pilot. And that system has been reaching its operational limit. So the FAA tasked MIT Lincoln Labs to design a replacement for it. And they used heavy-duty Qt artificial intelligence technology, such as Markov decision processes, to figure out how to help pilots. And then it was dropped in our lab to look at the safety of it. And here's one of those scenarios where our aircraft in relative coordinates is down here. Another aircraft is down there, and we need to figure out if we tell the pilot to climb, is this going to be a safe maneuver? And of course, the pilot could have been climbing, but could have decided to initiate a descent maneuver to duck underneath the other aircraft. And after some time, there's delay of at most delta seconds, typically 5 or 6 seconds. Does the pilot respond to that and say, oops, it told me to climb, so I guess I should initiate a climb maneuver, which the pilot may do in any way that the pilot sees fit? And then your challenge at that moment is to predict whether every possibility of these actions are going to keep the aircraft safely separated. In fact, you need to know this before they take off after every circumstance. And the challenge is that that's a large system with 5-dimensional interpolation regions and 500 billion different cases to look at. So it's kind of hard to verify flat out. So what we did instead is identify symbolically safe regions for the system and then prove their safety. And then later on, so that was done in KeYmaera model, and then later on compare them to the real implementation, which has the good news that the majority, 98% of the 500 billion regions of the system are provably safe. But the downside is that about the remaining 15 billion are counterexamples, such as, for instance, the following one, where our aircraft used to be climbing, the other aircraft used to be descending, and for some reason, that version of the ACAS X system that we looked at said, do not climb, which has the downside that if the pilot listens and indeed does not climb, then you have produced a collision that otherwise wouldn't have happened if both aircraft would have kept on doing what they're doing. And that's the kind of help that humans do not appreciate. If a computer helps them by telling them do the following and then there's a collision, that's not a good scenario. And then so the FAA said 15 billion counterexamples is a lot. Is there something you can do to reduce the number? And we looked a little bit further and said there's like the most challenging counterexamples are the ones where you cannot even make them better later on anymore. That means they're advisory, which if you do not reach the right decision right now, there's no second chance for it. That led us to study cases such as, for instance, if an aircraft receives a climb maneuver and the ACAS X later on said, you're not climbing hard enough, you need to climb some more in order to jump over the other aircraft. That would be a safe maneuver. Climb and otherwise later on say, sorry, I said climb, but I meant descend. The pilot does descend instead, which of course causes panic in people, right? If you think of the circumstance, if you don't reach the right decision in the next 6 seconds, you're dead. Right? And then the machine tells you climb, and later on it tells you descend. That's a panic-inducing moment in any sane human being, obviously. So that means these are really critical situations. And again, we analyzed them in a KeYmaera model, and now the good news is a lot more of those regions are safe. The bad news is about 1 billion counterexamples still remain, such as this one, when the aircraft used to be descending, and then neither climb nor descent decision at the end prevents collisions. The aircraft are still too close and will end up colliding. And that's one of those about 1 billion counterexamples that exist in those cases. And a little bit earlier, it would have still been fine. But of course, I would prefer earlier warnings than that one still. But that's one way of getting the number of counterexamples down. All right. And never mind that you could generalize this with games if you're super curious about it, different intruder actions, and read our recent journal article about this as well. More generally, what is it that we do and what is it that we provide as a technique, principles, and tools for the world? Well, it's differential aiming logic for multi-dynamical systems. So let me get to my favorite cyber-physical system, my favorite autonomous system, which is the WALL-E robot, in case you watch the movie. And in that one, you say things like, all behavior of my WALL-E robot are such that WALL-E's position is not the obstacle's position. And that means no matter where the WALL-E robot is moving to, WALL-E's position, which will be different as a function of what decisions the WALL-E robot reaches, will still in all of the states you reach be different than the obstacle's position. Now, of course, you cannot just put a real robot inside a logical formula and do things to it, right? Robots don't fit into logical formulas. It's a very sad fact of life, but you can write down a model for it instead. So here's a very simplified example where you say all behavior of a system that repeatedly checks if a certain set breaking condition as a function of the position and obstacle's position is true. And then if it is true, I guess you should be starting to brake because that's what it says. So you put a negative value into the acceleration variable. And after that discrete control, do you follow a continuous differential equation for a certain period of time? A differential equation that here says the derivative of position is velocity. while the derivative of velocity equals acceleration. Oh, hey, and the acceleration comes from this decision, which sometimes is negative, right? And that you do repeatedly. And if the system would be a little bit more complicated, you could typically have behaviors such as braking. Oops, it's good again, accelerating, braking. Oops, it's good again, accelerating, braking, accelerating. That's a typical acceleration trajectory over time. Here would be the corresponding velocity curve. So decreasing velocity, oops, increasing a little bit, decreasing, increasing, decreasing. And here's a typical position plot as a function of that. But of course, the position is now the one that can never be the obstacle's position, because you would be unhappy if your Wally robot collides, because the sensors get damaged, and Wally doesn't like that, right? Well, now you have an intuition for this differential logic formula, and it would be fair of me to ask, is this now a true formula? Is it true under every circumstance that all behavior of this particular Wally model are such that the position is different than the obstacle's position? And the answer is, of course, no, because you need some assumptions, but logic is great at managing assumptions. So you could start out by saying, if in the beginning you start collision-free, otherwise you will not forever stay collision-free. Oh, and if your brakes work, and some other assumptions like that, then will it be the case that all behaviors of the Wally robot model are such that you're collision-free. And by the time that is the case, you have a true formula. And of course, the true formula is then next in need of a proof that it is really a true formula, rather than just me standing here and waving my hands about it, right? Okay, and that's exactly what's coming up next. So more systematically, in differential logic, do you have a programming language of hybrid programs where you can write down discrete sudden changes, you can test conditions, you can very importantly, write down differential equations. You can write down a differential equation that says x prime is a function of x, and evolution domain constraint, never mind about them too much. You can write down choices. For instance, my system has a choice to fly up or fly down, or the other aircraft has a choice to fly up or fly down. You can write down sequential compositions. First I fly up, then I fly down. You can write down control loops that say I repeatedly reach a decision to either fly up or fly down. And with these, can you describe the system dynamics, right? Purely locally, mind you. And in the differential dynamic logic formulas, can you then state expectations about them, or safety conditions, or liveness conditions? So for instance, this is all further logic of real arithmetic. The exciting part are the box and diamond modalities, where for any hybrid program alpha formed like so, and for any differential logic formula P formed like so, is alpha box phi saying that all behavior of alpha keeps us happy? Whereas beta diamond is saying there is a behavior of beta that takes me to the goal. Or you could nest them. There is a behavior of beta that takes me to a goal of the form that all the alpha behavior is safe. So there is a beta behavior so that all the alpha behavior keeps me happy. Or you could sprinkle in other logical connectives, or universal or existential quantifiers, or implications and ands and ors of the world into this. It's a rather rich language with which you can state questions. But of course, you shouldn't just be stating questions unambiguously in logic and mathematics. You should also be answering them. And, this is where, never mind that. This is where you see some patterns, such as safety is typically expressed by saying, if I start in the region Q, will all the behavior of alpha keep me happy? For instance, will I always stay inside the red region? Liveness is typically stated like this. If I start in Q, will I eventually, if I just wait long enough, reach the red region, right? Will I eventually get to my goal? Will I eventually go to Paris when climbing on the train, which was a very real challenge I had yesterday? Stability would be like so. So for every epsilon, there's a delta, such that for every position, if you're close enough to 0, then all behavior will keep me close enough to 0 for different closeness values of delta and epsilon. This is stability. Attractivity, for instance, you can state like so by saying there is a delta, such that for every position, if you start close enough to 0 in the delta sense, then for every closeness value that you have, if you wait a little while, there is a behavior of the differential equation such that all future behaviors of the differential equation will keep you epsilon close to 0. So, and with the two of them together, stability and attractivity, can you state asymptotic stability? The point is, lots of questions about dynamical systems can be naturally phrased like that, unambiguously. And now, of course, they're in need of answers, which is where we come for proofs for dynamical systems rather than just stating expectations for dynamical systems. But that's easy because one of the most important properties of what you saw is that everything has a very simple compositional semantics. Everything is a simple function of the meaning of the pieces, and you can exploit that for proofs. So here we go. This is, for instance, the axiom of choice. All right, the axiom of non-deterministic choice, which says that all behavior of a system that has a choice of fly up or fly down is safe if and only if all the alpha behavior is safe and independently all the beta behavior is safe, right? And by using this equation of truth, this axiom from left to right, do you decompose one question about a bigger system into lots of sub-questions about subsystems? And they are individually easier, and you can only, even if it's a terabyte, you can only decompose a system finitely often. So this is a well-founded reduction by using the axioms from left to right. Ordinarily in science, you study either the laws of logic or the laws of physics, and here you do something even more cute. You study the laws of logic of the laws of physics with which you can describe your system and then establish truth for it, because, come on, these are equivalences. These are equations of truth. Using them from left to the right preserves truth. Okay, never mind those pictures. The point is you have a very strong principles for those. For instance, sentence completeness, everything that you prove is true, and you can prove everything that's true from just elementary properties of differential equations or discrete dynamics. Check out those references if you're interested in this. And how do you prove differential equation properties? I guess that's one of the challenges, right? If every proof reduces to a question about a differential equation, how do you prove the question of the differential equation? It seems like a very important question to ask. So here's two examples. If you start somewhere inside the green hourglass-shaped region, you will forever stay inside the green hourglass-shaped region if you follow this differential equation. Never mind what it is. I painted it in the background of the picture for you, right? So for instance, you will follow this spiral path here. And yes, indeed, in this case, it is easy to see that this particular trajectory stays inside the green region, but the question is, does every trajectory starting from every point in this region forever stay in it? And that's a little subtle if you put your attention down there, for instance. And the point is, of course, you wouldn't just like to be able to draw those pictures and squint your eyes and hope for the best, but you would like to have a mathematical proof, which is particularly evident in higher dimensions because it's hard to plot. But even in that dimension, it's better to know for sure than to just plot and hope for the best, right? And this is basically Henri Poincaré's challenge from 1881 to study differential equations via the differential equations rather than via their solutions, because solving a differential equation sounds like a good thing that mathematics training tells you to do, but it's a very bad idea because the whole point of a differential equation is that it is easier than its solution. So if you analyze a differential equation but first solving it, you have undone its descriptive power. You've made the problem worse. So you need to analyze differential equations via the differential equations. Oops. And that's exactly what Henri Poincaré called for in his qualitative theory of differential equations in 1881. And we figured out a good answer for that, which is the following, that indeed we can prove every true equation about a differential equation just by logical proof in very simple ways. So by proving that always after a differential equation is an equation true, if and only if another equation is true. Never mind the evolution domain constraint Q, that's not so important for my story. Check out the Licks and the JSN papers if you're curious about more of those, and generalizations of it, etc. But in a nutshell, that says always in the future along a differential equation will an equation be true if and only if another equation is true right now. And whether an equation is true always in the future, oh boy, that's a hard question, right? This is a prediction of the future. And as Niels Bohr said, predictions are difficult, especially if they're about the future, right? And here, this is proven to be equivalent to the question whether an equation is true right now. And checking that is kind of a triviality. You just plug in the current system values and see whether you get out 0. That's easy, right? But because we can prove the two to be equivalent, do we know exactly that an equation will forever be true in the future by just asking a question about the now? And since it's equivalence, will we also be able to say no to the question whether the equation will be true forever in the future? And it's like that also for arbitrary first-order logic of real arithmetic formulas, where you also have a corresponding completely syntactically provable equivalence principle. So that way you can prove every true invariant of a differential equation, if true, and to disprove every false invariant of a differential equation, if false. So you have a pure logical decision procedure just by rewriting, which is super cute. Okay, that gives us a very strong technological basis. And what can we do with that? Well, build technology for safe artificial intelligence for our autonomous dynamical systems on top of that. So lots of applications are possible. We looked at the Federal Railroad Administration's train control safety system, the Federal Aviation Administration's air traffic control system, the next generation airborne collision avoidance system, car control, robot control, etc. All of these things are possible with the same technology underneath because the technology is so universalist, right? It really applies under all those circumstances, and you have theoretical completeness proofs. So that means you have a proof if and only if true, which is a strong property to have. But how do you interact with the world? So how does this system then give you some kind of ideally provably good interactions with the neighborhood where there's learning involved, etc.? All right, here we go. So you have a system and it's proved okay in isolation, but now it starts interacting with the world, for instance, in reinforcement learning, where you act in the world, make an observation, such as, should I be accelerating or braking, right? You try it out, you say the acceleration caused a crash, so that was a bad idea to be doing that, right? Sadly, you lost one car in the process, so it's a bit expensive. Or maybe one simulated car, which is a little less expensive, right? Or you brake and figure out that it was a good idea, and you read down a policy by reinforcement learning from that. What do I do under those circumstances? I guess whatever I am confirming, I have confirmed. All right, not my laptop, so I don't feel personally responsible for that one. All right, good. So in reinforcement learning, do you speed up or slow down, right? And the question is this good or bad? And the point is, we know from our safety proofs which decision is safe when. So what we can simply do is monitor whether the decision that a reinforcement learning agent reached is a provably safe one. And then rather than having to wait until, several minutes later, there is a collision or there is not, at which point you then need to propagate back. Oh, the collision was a bad idea, but which decision before the collision caused this bad idea to happen? It's usually a couple of seconds ago or a couple of minutes ago, right? That's a very slow, very sample inefficient propagation process. And also, you need to be lucky that a collision happened. Wait, you're lucky that a collision happens? Well, the point is, if you're trying to establish the safety of the system, if you lucked out this particular time because all the other vehicles went away so that no collision happened, in reality, is that a good thing? But for trying to figure out whether the decision was a safe one, is this a bad thing? Because you're desperately trying to figure out all the corner cases and whether something could possibly go wrong. So if in, let's say, your simulation, no collision happened, that would actually be bad, right? So it needs lots of samples and lots of circumstances until you know. And if you do this with proof instead, we know right away from that moment, if, dear reinforcement learning agent, you reach a decision, acceleration, that is not a provably safe one, so that means there is a potential future where you could get in trouble with this, we will tell you, don't do that right now, right? And that's a much better signal that you have at that moment. We veto the decision if it's possibly an unsafe one. And there's no need to wait for the disaster to strike and then slowly propagate back future problems. So in that sense, you have the best of both worlds, because differential dynamic logic benefits from the reinforcement learning optimization. In verification, can you focus on safety and say optimality? I don't know, not my problem. I don't give a damn about it, right? Because that's what the reinforcement learning agent is contributing. In reinforcement learning, can you benefit from the differential dynamic logic safety signals? Because reinforcement learning isn't really good about establishing safety anyhow, right? So if you do proofs for that instead, you have a safety signal that the reinforcement learning agent can contribute from. And with that, you can prove, check out these papers if curious, that this converges to a safe policy if the differential equations are accurate, and you have very graceful recovery outside if the differential equations are inaccurate, using something that we've called quantitative modelplex, but never mind. You can generalize to lots and lots and lots of models, but that's, I think, where you're better off reading up about this on your own. Because I would like to get to the next challenge. That was, okay, how can you make use of this for reinforcement learning purposes? But how can you make use of this for neural network learning purpose? So if you have a neural network control system, so if you have a car that's being driven by a neural network, it's speeding up and slowing down and things like that, well then, for neural network verification, are there basically two technologies out there. The one is open-loop neural network verification, which is just ignoring the physics entirely. And then you can ask questions such as, if for instance, the easiest example is, if I'm very far away, I do not need to act. That's a good sanity test on your neural network. If you're far enough away from disaster, no interference is necessary. But just because a neural network satisfies that if you're far enough away from disaster, you do not act, that doesn't make it safe, right? Because it's more important that around the area where trouble is, you reach good decisions, and the next decision will be a good one, and the decision after that will be a good one. It's eventually an inductive property. So with open loop neural network verification, can you not answer it except for sanity checks, right? For closed loop neural network verification, do you take the physics model into account? But if you do this reachability style, then the problem is that you can ask questions such as, will there be a collision in the next 5 seconds? And that's a good thing to be able to answer. But would you personally get in a car if it came with the guarantee that you do not die in the next 5 seconds? Probably not, because you would like to have a much longer term guarantee, and that's where the error keeps on getting completely impossible on reachability analysis. So what we do instead, we say, aha, okay, but I guess we have proofs that our models are safe, but they're not proofs about the neural network. Can we maybe reflect the proof of the model in the proofs of the neural network so that we establish corresponding proved properties about the neural networks, then reflect, and that's what we call the Versailles principle. It's a good thing to mention in Paris because of all the mirrors in Versailles. So we're reflecting this in the mirrors in a certain sense. We're reflecting the safety proof of the model into what does that mean in terms of logical, nonlinear real arithmetic formulas about the neural network, that then an automatic verification tool establishes by proof for the neural network, where there's also generalizations of DPLL of theories, principles, in order to make that work in a if and only if way, in a sounding complete way, for nonlinear questions about reducing it to linear regions that you can then handle with SMT solvers in an if and only if way. In a nutshell, what that makes possible is, for instance, in the neural network version of the next generation airborne collision avoidance system, can you exhaustively characterize all the counterexamples, so all the cases in the state space where the neural networks give you unsafe decisions. Here's some of them where for level and tutor flight, this is a case where the neural network gives you an advisory to climb, which, as you see in this counterexample region, is a bit of a bad idea to do, right? Here also for those circumstances, and you overall get an exhaustive characterization of all the counterexamples that you have in the system consists of 8 neural networks for 8 different decisions, and 6 of those are unsafe, and you have an exhaustive characterization of the unsafety, and 2 of those neural networks for 2 of the possible decisions that apply sometimes, but not always. Do you have safety, but only for level and tutor, only for if the intruder keeps on keeping a steady altitude. If the intruder keeps on flying up or flying down, then it's also unsafe. But you have an exhaustive characterization of those, right? Also, for instance, for cruise control in a neural network cruise control system, you have an exhaustive characterization of all the cases where the system is unsafe, and then you can do something against that, right? Because you inspect the exhaustive counterexample region and say, aha, all the counterexamples are when the relative position is small. So maybe just overwrite the neural network whenever the relative position is small and do something else. And then you can craft a provably safe system out of that that's mostly, but not always, listening to the neural network. All right. Here's another cute generalization of what I told you about, which is, well, all of that was a person is being clever, designs a system, and then a person is being uber clever, analyzes the system, and then you have proof. Although in reality, that's not how it works. In reality, the way it works is someone is very clever, designs a system, and is very convinced that the system was designed in a safe way. Then you analyze the system, and what happens next? It has never been safe. Not a single system we ever looked at has been safe, right? Sometimes the problems and counterexamples are very tiny in some corner of the system, but they're always somewhere. So part of the verification challenge is to figure out when is the system not quite right, and what can you do to fix it. And that's a very good approach, but the opposite approach is to hope that maybe you could specify what you would like the system to do, and then synthesize a control algorithm that comes with a safety proof solving the control challenge. So basically saying, I wish there was a car control that is safe. And then the system goes off, synthesizes a control for it along with a safety proof and says, here it is, this one is safe. By the way, the example I just stated, is that a good way of stating car control? I wish there was a car control that does not have collisions. Please synthesize something like that. Is that a good idea? No, it is not, because the solution would be just don't move. That's a very safe car controller, but also a very useless car controller. So rather than that, do we synthesize control envelopes? So not a single control that is safe, because then you would have to go, oh, damn, I need it to be safe, oh, and move, oh, and be fuel efficient, oh, and also not be bad for the environment, oh, and blah, 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 blah. It's a very difficult challenge at some point. Instead, what we say, we want the set of all safe controls, the set of all collision-free controls, that's synthesized. And within this, can then an engineer say, aha, within this, let me also be fuel efficient, or let me get to my destination, or all of these additional properties that are important, but not all can be stated and done formally. So this is CESAR, control envelope synthesis via angelic refinement, where you state a property and then automatic logic-based technology jumps off and figures out under what circumstance can I accelerate, if that's the question. Under what circumstance can I brake, if that's the question. What happens in the differential equation, how do I preserve collision freedom, etc., and so on. And that's using games technology. So that also shouldn't be a complete surprise, right? Because the answer to synthesize a system that is safe and that is maximally flexible, so the set of all safe controls, is playing a game against an opponent that was trying to make you collide, for instance, right? And if you figure out the winning strategy in this game, have you figured out how to, in what region can you have a safe control? So that's precisely what the base idea, along with lots of logic and symbolic proofs in the CESAR approach. Check out the ACAS paper from last year if you're curious about this. Okay, you can generate invariants automatically in the Pegasus invariant generation tool. Also, that's a mix of using symbolic techniques and numerical techniques. So for instance, here's the green is an initial region and the red is a bad region in the system, and you would like to find an invariant that is telling apart the good and the bad regions. And it's very cheap to say the blue region is an invariant, but it doesn't help you establish safety because, well, here's lots of unsafe states inside the invariant. Then it's very easy to say, aha, the positive x coordinates are an invariant, but that's still not safe because it includes all these bad red regions. Once you figure that out, you know, oh, once I know that this is an invariant, do I also know that y greater than 0 is an invariant? So now you're in this corner of this orthant of this system, but that still includes lots of unsafe states. And then Pegasus goes off in the third step and says, aha, now I know that these are invariant, so I stay inside this region. Do I also know that this is an invariant? And all of a sudden, have you managed to safely separate your initial and your unsafe states? And you've established a completely automatic proof of safety of the differential equation. In fact, even in this particular case, you even found a barrier that way. That's what Pegasus does. Check out these FM papers from a few years ago, and never mind the experiment. Another good thing is, well, if you have lots of safety technology, but you would like to run it on a real robot, there's additional challenges, unfortunately, right? Important challenges, unfortunately. And isn't it a shame that you have lots of proofs on the dynamical systems level, but they all evaporate by the time it reaches execution? Yeah, that's a shame. So in a verify pipeline, do we go from the high end to low end with provably correct machine code, such that every step along the way was somehow theory improved? That's the good news. The bad news is that we needed the separate theory improvers for the job, because I haven't found the theory improver yet in which you can simultaneously do a good job proving properties of differential equations. That's what KeYmaera is very good for, proving properties of hybrid systems, proving properties of dynamical systems. But KeYmaera is honestly a horrible prover for proving correctness of register allocation, right? Whereas that's something that Hall 4, for instance, is very good for. And wait, the two of them don't talk to one another. So Isabel Hall is a good bridge between the two. Anyway, but modulo the fact that we have different theory improvers along the way, do you now have a a pipeline taking you from one way to the other. And the analogy is basically, if this is your model and you would like to get to the safe cyber physical systems implementation, there's lots of stupid low-level proofs standing in your way, and the way to get around this is to use the verify pipeline to go from the beginning to the end, dodging the stupid low-level proofs that you would otherwise have to do. So that's also very interesting technology. Let me summarize this brace through lots of cyber physical systems, dynamical systems, autonomous dynamical systems, technology that is all centered and revolving around logic in the following way. You've seen everything revolves around differential dynamic logic, which is combining dynamic logic and hybrid programs, giving you, on the one hand, strong analytic foundations, because, hey, at the end of the day, you've seen them. These are very simple sound axioms, right? Such as every behavior of a system that has a choice is safe if and only if every behavior of the subparts is safe. Come on, decomposing systems like that is obviously safe. I'm never doing a mistake if I work that way around. And I'm preserving truth because they're equivalents. I do logical rewriting to figure out the answer, right? And that's precisely the basis for lots and lots and lots of other technology that I've shown you. So that's also where a lot of the practical roll-up-your-sleeves reasoning advances come from, implemented in a KeYmaera Theorem Prover and